So in this video, I want to kind of wrap up the issue of protein sorting with three sort of random bits that I haven't covered yet, and I wanted to get those out of the way. First one has to do with the energy of co-translational translocation. And it's going to involve a protein called BiP and a phenomenon called Brownian ratchets that I want to take a little bit of time to describe. So where we begin is with the translocon from a previous lecture, and the ribosome nascent chain attached to the translocon at the ER membrane, like so. So there will be the exit tunnel and the nascent chain coming out of it, like so. And we normally think in terms of the energy of translation as being provided by the translation reaction itself. But in the particular case of co-translational translocation, that's not sufficient. There is Brownian motion acting on the nascent chain in the translocon pore, and if this were all that was involved, then what would happen is that the ribosome, which is weakly attached to the translocon, would just pop off, and that potentially could lead to the nascent chain just zipping right back through. And as you will know by exam 3, we've gone to a lot of trouble to get that nascent chain there. So we don't want to have that process just reversed at random. So it turns out there is a solution to that problem that also solves another very important problem that we haven't dealt with. And that is the fact that the interior of the ER, the lumen of the ER, is an aqueous compartment that the nascent chain is emerging into as an unfolded polypeptide. So I'm pretty sure you know where I'm going. There are going to be exposed hydrophobic patches, and those could potentially cause misfolding. The ER is a very, very, very crowded environment. If anything, it's more concentrated in the cytoplasm. So all those issues of protein folding that we had to deal with in the cytoplasm are still going to be there in the ER. And again, you could probably guess where I'm going, especially if I go ahead and draw what is sitting on the luminal side of the translocon pore, basically just waiting for the now luminal nascent chain to emerge. And that protein looks like this, and is, as I'm sure you know, an HSP70. And I mentioned that HSP70s is a term that describes a family of proteins. Most of them are just called HSP70 or sometimes HSC70 or some version of the same thing. But in the case of the ER, the HSP70 gets its own name, and it's referred to as BiP. So otherwise, it does exactly the same thing that HSP70s do. It binds to hydrophobic patches using that beak. It undergoes ATP hydrolysis-driven reaction cycle. But in this case, there's something in addition to the unfolding, refolding job that a standard HSP70 will have to do that is unique to BSP, to BIP. And that is to solve the problem that I started with, the energetics, essentially, of the co-translational translocation. By putting BIP here and having it do what it does, which is to bind, release, bind, and release, what you're doing is preventing the Brownian-based diffusion of the nascent chain back in this direction. So you're essentially causing the movement associated with Brownian motion to only be in the direction that you want it to go, which is into the interior of the ER, into the lumen of the ER. So this is an example of something that's referred to generically as a Brownian ratchet. And that phenomenon is described pretty nicely by Wikipedia, and I took this image from Wikicommons. If you Google Brownian ratchets, if you Google image Brownian ratchets, you'll see a million of images like this. this is, I think, the best of those images. And what it's being shown here is a schematic of what Brownian ratchets are in general. So first of all, here's Brownian motion. These are atoms bombarding on something. In this case, it's this propeller. So if you leave out this part, then that Brownian motion would cause that propeller to go back and forth in no particular direction. As this atom hits, it would push the rotation in this direction, and if this atom hits here, it will cause rotation to be in this direction. But if you imagine a device that is, in this case, a ratchet that prevents movement in this direction, now what will happen is Brownian motion will cause the propeller to move continuously in this direction, because this direction is blocked by this ratchet, right? So it'll be as if you've got some perpetual motion machine using Brownian motion to cause the rotation of that propeller. In fact, it's not a perpetual motion machine, which are not allowed in thermodynamics because of this weight device. So essentially this is providing an energy input that is used to control the direction of rotation that is driven by thermal energy, which is what's causing the Brownian motion. The bombardment of atoms comes from the energy of the sun, basically. So you're harnessing the energy of the sun by this device, and that's what Brownian ratchets do in general. So in this case, the energy of this device comes from ATP hydrolysis, binding and hydrolysis, which is causing this beak to close and clamp down on the nascent chain, and that's what's preventing the Brownian motion in this direction. So it's essentially doing what this ratchet is doing in this diagram. And you let that process go, what you'll see is the very smooth, continuous movement of the nascent chain into the lumen of the ER, as if it were energized by the translocation device. In fact, it's energized by the sun, and that energy is made unidirectional by the Brownian motion provided by the ATP hydrolysis of BIP.